on this computer. Okay, I think that should do it. Yeah, looks like it's going. So hopefully that did it. Okay. Anything else, guys, before we get started? So let me get to the point where we stopped. I think we stopped at gradient last time. So these, we described vectors and scalar fields in different coordinate systems. And then we started talking about vector operations. The first one being, I think the first one was gradient, which is, one of the things I mentioned, and it bears repeating, is that you got to be really careful about, and you'll see me making this mistake in the lecture all the time, I'm sure, is be careful. Some operations are making, whoops, sorry guys. Some operations are making vectors into scalars into vectors, and some operations are doing the reverse. So the gradient is basically you're taking a scalar field and doing this gradient operation on it, and the result is a vector. So, and in Cartesian coordinates is the easiest thing to remember gradients on, and it's basically this guy. Oops, it's not really thick. Let me minimize that bad boy. Okay, is this guy here, basically. So if this gradient operation, you're taking the derivative with respect to x, derivative with respect to y, and derivative with respect to z of a scalar field, and then multiplying each one of those respectively by the unit vector in that particular direction. What am I doing here? I'm sorry, guys. Okay. All right, so that was gradient. Now the divergence of a vector field. So the divergence is more a matter of, first let me tell you guys what a divergence basically looks like from a physical standpoint. So it really, this is kind of so I'm just jumping up here in the slide where it's defining the divergence as this surface integral. So notice that, this integrals, we have an integral sign. It's got the circle. The circle means it's a closed surface. That means there's no gaps in that surface, some surface S in this case. And we're integrating this vector field all along that surface. So we're integrating the vector field, basically we're any kind of surface, right? And it's the divergence of the vector field is when you take that integral and divide it by the volume in the case where the volume goes to zero, in the limiting case where the volume goes to zero. So that activity is as if, sort of the analogy for me as a closing fist. So imagine, very small fists closing all over space or along any surface integral you'd like to define, and whatever is enclosed in that space is what is the meaning of is divergent. So as you'll see in a few minutes when we start talking about Maxwell's equations, this divergence basically, using this equation basically tells us how much charge we have and that we have unit charge in some space. So as you basically, it's this you can imagine it being this closing, taking a surface integral and of a closed surface and dividing it by the volume that's enclosed by that surface. Okay. And in
Por ejemplo, eso habrá sido.
was there a question, guys? Or maybe it was just background noise. So if in Cartesian coordinates, the divergence of a vector field is the derivative with respect to x, y, and z of that field in the respective directions. So remember that we said the gradient is the result of the gradient operation is a vector, and you do the gradient operation on a scalar field. This is the reverse. So you do this operation on a vector field, and you end up with a scalar value, which is what's enclosed in that inside that value. Okay. So if the divergence is, if this divergence value, after you do all that, if this value is a positive value, then that means this vector field is pointing out from your surface. Okay, these are four positive values of divergence. And if you get a negative value of divergence, that means that the vector field is pointing inside. So negative value of divergence is if the vector field lines are pointing inside this. Okay, so that's the definition of divergence. And let's see, what else do I want to say about this? So, another thing that's, going back, the flux density of a electric field is defined as sort of the total amount of that vector field that's perpendicular to the volume whose flux density we're trying to define. So the flux density is just equal to that vector field with the dot product of that field with the unit vector that is perpendicular to the volume. Okay, that ends up being the flux density of any kind of vector field. Of course, this is like telling us, it's using the capital E vector form. Remember that in these slides, the capital letter in bold implies a vector, basically value. Okay. So that's why do I keep doing that? Sorry, guys. Okay. So that was divergence. And there's this useful theorem, which once we get into electrostatics, which is the next set of slides, you'll see the usefulness of immediately, which is this thing called divergence theorem. Basically, it says if you take the basically the coming back to this, equation, if we kind of take it in the other direction, we end up with this equation, which we can use, as you'll see, to end up useful in getting Gauss's law, as you'll see. So del dot E. Okay. So nothing, I guess I don't know what to say about this one. It's just it's a theorem. I don't know if I have any visuals or sort of any way to think of the physical aspect of this. It's a useful equation. Again, you'll see it in a few slides going forward. I'm gonna skip over these examples. And so, okay, so we come now to the curl operation. Okay, so the curl operation is something you do on a vector field, and you end up with the vector at the end result of doing the curl operation. Okay, and the idea is that you're taking the integral around a closed, this is a closed line. Okay, so notice here the delta L, we defined L earlier in these set of slides as unit vector in the direction of a line. So for example, if you were integrating a line, you're doing a line vector around the loop at any point along there, you would have different delta. Here the DL value would be like that. Here the DL value would be along like that. And then as you're going around this thing, you're basically integrating the vector field along that. So the definition of a curl is that you are doing that operation along the line and then dividing that by the limit of the surface that that line is enclosing. So that would be, in this case, it could be the surface. Okay, that would be 1s. So that would be s. S is one possible s. But notice that's not the only possible s that this line could be going at the lip of. So there could be, like, let's say if I had an s that was more like a dome, still the lip would be defined by the same line, but it would be a different s. But it's basically the limit of that s going to 0. You're dividing this line integral over that surface as the limit of the surface goes to 0. And the direction of that resulting vector is in this direction, is that's a unit vector in a particular direction. Okay, so now imagine if this B was the magnetic field. Okay, what you could do is, if you had a line with a current, so if you look at the right side of the slide, okay, so this is line with the current going through it, and if I took a path around, I don't know if you guys can see my green drawing of the circular path around that line, so I can take any contour C, because what I'm doing is I'm going to sort of shrink that contour C to something small. That if I integrate completely around that contour, then what I get is the current going through this. And that value of the curl is the current going through it. And the direction of that is in the direction of the current. So let me give you kind of a visual for that. So when we were doing this divergence of a vector field sort of, if you want to imagine what that function is we were, you know, like sort of grabbing like a closing fist around whatever volume. So like this fist, my actual fingers are the surface. Okay, and what the fist is grabbing is a volume. Okay, so what I'm doing is if I'm taking the divergence of a field, is I'm sort of going around the field and grabbing on, closing my fist to see what's, and then I'm going to check to see what's inside, what's inside, what's inside, what's inside. So it's a surface enclosing a volume to see what's inside. So the visual for the curl to me, of especially when it comes in the form of a magnetic field, is more of like a lasso. Imagine if I had like you know, I was throwing a lasso around. So it's a line. So just these two fingers, my trigger finger and my thumb, are like a lasso that I'm kind of grabbing all through this vector field to see what's in the form of a line that I can grab. So some places there is no line that I can lasso onto, and then some places there is. Notice if I was trying to close my fist around this pen, like I wouldn't capture the entire thing. Okay, so the divergence would give me basically what I could capture along this pen. But if I'm throwing a lasso around this pen and closing, I can kind of capture what's going around this, through this pen, in the direction of this pen. So that's like a visual, I guess, for me of the curl operation versus the divergence operation. And the curl also, just like there was the divergence theorem, is like a useful equation for divergence, and so is Stokes' theorem for the curl, which is basically it's equating the curl of a vector field with taken around through a surface to the integral of that same field taken along a line. Okay, so both, you know, I'm trying to also get you guys thinking about why this equation, say divergence theorem, why is this useful? The reason is, like, sort of like, why is it useful in my mind? Not necessarily mathematically, but from the standpoint of us calculating this thing. It's relating a volume integral to a surface integral. And to me, it's always easier, you know, when you're working at a lower dimension, this mathematical things are a lot easier than higher dimensions. So it's always harder to do a volume integral than it is a surface integral. So if you have a way to substitute some kind of a surface integral for a volume integral, it's like a big win from being able to calculate a problem. And I think the way I look at Stokes' theorem is a similar thing, in the sense that here with Stokes' theorem, it's basically relating a surface integral to a line integral, meaning that it makes it easier, instead of doing an integral along, say, all the surface, which could be more difficult, you're doing your integration along just the contour surrounding that surface. Okay, or sort of defining the edges of that surface is a better way to say it. Now notice that this same contour, this was a little confusing to me when I first look at this. This contour C is, when we're looking at the divergence theorem and you have a volume, there's only one surface S that defines that volume. You have a, you have a volume. That surface is what the surface is. But in the case of relating the contour that defines the edges of a surface, you can have different surfaces being defined by the same contour, by the same edge. So I'm trying looking at something that I could use to, no, I don't have any useful props here, but if you can imagine, if I had like a contour that's like a circle, okay, and there's like a sheet propped right through this thing, just flat sheet that's spread tight. That's one surface, but that you could have a like a rubber sheet that's by bowing out, and it would still have the same lip. And so both of those are defined sort of by the same contour defining their lips. Okay, so it's like there's a bunch of different ways of defining that. Okay, the Laplacian operator, it's, I'll just, it is this, like, to me, it's like a second order differential in sort of vector space. So it's an operation that happens on a vector and gives you a scalar field. I'm not sure we're gonna see that till, we're looking at antennas, etc. So I think initially, like, mostly the divergence and curl are the important functions to think about. Okay, some examples here. This equation. So okay, so I'm done with that set of slides. So now we're gonna go to so that was like the leftover from last lecture. So now I'm gonna be going through this lecture. So the lecture is about electrostatic fields. Okay, so I think at the beginning of the class and a couple of times I wrote you guys this Maxwell's equations down, which are the, whoops, change this to PDF version so it's easier to mark up. Yep. So these are the Maxwell's equations. Sorry about the little God light thing. This is from like the I call it the slides that the author provided. But this is Maxwell's equation. Okay. So these are all the equations, Maxwell's equations. It says it's relating. So now maybe we are a little bit more aware of what some of these things mean. So now look at this as a divergence of the electric flux. Gives you, now you guys kind of know at least the equation for that and what physically that means. A divergence means you are grabbing, you're closing your fist or closing a volume. And when you're closing a volume, this equation says when you're closing a volume of electric flux, which is this D value, what you find inside is the charge density, and we'll define all these things. And this is a curl operation. Again, we kind of learned what that meant in the previous set of slides. And the curl of an electric field is the change in the magnetic field with respect to time, the negative of that. And then the divergence of magnetic field is always zero, guaranteed to be zero. And the curl of the, this is the magnetic flux density, is the current density plus the change with respect to the electric flux density with respect to time. Okay, so let's first just think about a couple of things that we don't really aren't gonna change regardless, okay, that are easy to look at. But what I hope I just try to define it in a way that would be physical for you guys. Again, if you go look around the whole space that's made by this electric field or electric flux density D, which we'll define in a little bit, and you kind of close the volumes around space. At each point, if there you might get zero if there's no charge in that place in space. But if there is, the value of that integral will be, or the amount of the value of this divergence is the charge density that you find inside that volume. Okay. And more kind of another interesting thing is note that the divergence, the Maxwell's equations say that the divergence of a magnetic field is guaranteed to be zero. It's always, always, always zero. That means that if I try to go close my fist around the magnetic field, I always get zero. So there's no, what that says is there's no sources and sinks for a magnetic field. So for example, imagine if I'm trying to find the divergence. So not the lasso, but I'm trying to find the divergence of something that's bigger than my volume. So has no beginning and no end. So that's the thing about all magnetic fields are caused by currents, okay? And currents by definition are running in a loop. Oops. What happened? Oh, so currents by definition are running in a loop. So when you try to close your fist, I can close a lasso and grab something that's in a loop and capture it and get a value for it. But I can't close my fist around the loop. There's always the same value coming in as going out, and those two cancel each other out. So that basically guarantees that the divergence of the magnetic field is always going to equal to zero. Okay, so now after having said that, let's look at all these four equations, which are the sum total of the electromagnetic equations. And remember, we're talking about something called electrostatics. And what electrostatic means is static means something that doesn't change with time. Okay, if something is static, it means it doesn't change with time. So when we're talking about electrostatics, it means our derivative with respect to time is equal to zero. Okay, so what we can do is we would go through Maxwell's equations and set anything that has a derivative with respect to time equal to zero. So that means that the curl of E in my finger, it says that this curl of E value is just equal to zero. Okay, because dB dt is going to be zero. And this curl of H is also going to just equal to the current density J. And again, we'll define current density in a little bit, because the derivative of the electric flux with respect to time is equal to zero. Nothing changes with the divergence of D or B. Okay. And the other thing that happens in electrostatics is notice that basically there's no relation now between the electric field and the magnetic field. So the linkage between the electric and magnetic field were this equation and this equation, these two guys here and here. And as soon as we just say the derivative with respect to time is 0, the electric field is the electric field and the magnetic field is the magnetic field, and they're just totally decoupled, okay, under sort of static conditions when nothing changes with time. So, and also remember that what caused a wave, an electromagnetic waves, was that the electric and magnetic fields were coupled with each other, and a changing electric field would give rise to a changing magnetic field and vice versa. So in the case when nothing changes with time, you don't get electromagnetic waves. You don't get electromagnetic wave propagating in those conditions. You just have the electric field being the electric field and the magnetic field being the magnetic field. Okay, so this is sort of the condition we're going to be talking about, which is the condition where the two fields, electric field and magnetic field, are decoupled and there's no electromagnetic wave. So we're just going to use this, as you'll see. Let me just fast forward to why we're doing this. Remember the first part of the class, we were talking about transmission lines where each part of the transmission line has small values of inductance and capacitance, And in case of lossy lines, there were also resistors thrown in for each section of the line. And now what we're doing in the next couple of lectures is trying to figure out, at least in a few simple cases, how to calculate the values of capacitance, inductance, and these resistive values for the transmission line. So basically using electrostatics, we calculate these values and then we can plug them into the line and use them to figure out what happens when things aren't static, or when we're having a sort of a voltage and current wave propagating through this thing, through your transmission line. All right, so let's sort of talk about charge distribution. So we use this concept of charge density, in this equation here. So now I'm going to define it in this next slide. Okay, so basically charge density, when we have the sub V, means the charge density in a unit of volume. The units are in coulombs per meter cubed, or sort of unit of volume. And basically it says, if I take the charge over a volume and I look at the limit as the volume shrinks to 0, what is sort of the charge? How is the charge distributed? So you guys have an idea of density. And so, this is like if I had a ball and there was charges uniformly distributed to this, I could think of what would be the density in each unit, in each volume unit here, as these little cubes would shrink in size. And, might be the same everywhere, might be different, might be a function of position. And the total charge in a volume, so in this case, for example, if I think of the total charge, is the integral of that charge density over the volume. And again, this rho sub V, sometimes it's uniform, sometimes it's a function of position. But in all cases, the total charge is basically the integral of this charge density over the entire volume. And then we also can define surface and line charge densities, because these are more like pretend, because to solve problems, really, because in the real world there is no line. So if you notice this this equation is pretending that you have a line of zero width, which you can never have in the real world. But if you had, and there was a charges along this line, and the line itself was like zero thickness, you would get a charge per unit per line. Sorry, this is the line charge density. Sorry, pointing at the wrong thing. And then if you had a surface charge density, the surface would be like completely thin. There would be no zero thickness to the surface, and you could define the charge density as being whatever's charge is distributed on that surface. So that's the meaning of the charge densities. Okay, and in these cases, the charges are not moving around. They're just distributed in some way. And then we also have something called a current density. And as you guys, I'm sure you guys know, is current is sort of movement of charge over time. So if we were looking at sort of a volume of charge, so this kind of is part of the cylinder here to the right, and we were thinking about this cylinder moving along, this would have a certain amount of charge in the cylinder, and it would be traveling from left to right at a certain distance, which would be the current. So basically the change in current would be whatever's the charge density in that volume times whatever the the surface is, because this is like giving the volume. So this is giving this. So sorry, it's easier to look at it this way. This and this are, this is the surface, delta S prime, and delta L is the width. So between multiplying these two values, this gives the volume of my cylinder, and I multiply that by the charge density in the volume, and that gives me the total charge here in that cylinder, and that's kind of what's moving through. And basically you could have any kind of surface. It doesn't have to be cylindrical, as long as you define the surface delta S to get the current density. Now, one thing you can't do though is, for example, this is what this drawing is supposed to show, is let's say I have a current density going through this wire. I can't fake and increase that current density by doing a diagonal cut, and therefore sort of artificially increasing delta S, because what you'd have to do, the way you define the charge, is you're saying that you're taking the dot product of the direction of current flow with the surface. So even if I cut the surface flow like that, sorry, the surface cut diagonally across, I'm trying to figure out the component of charge flow in this direction. And that basically gives me the same charge density as if the surface was like that, because of that dot product. Okay, and then, so that gives me the current, and the current density is basically the amount of current per unit surface, basically, that is going through. So that, like, if I wanted to have the total current going through this wire, I would have to integrate the current density along whatever surface is the wire is surrounding basically the wire. Okay, so current density, the reason it's useful is because, let's say I had a I guess it's like, I use it all the time in terms of the current density, because a lot of calculations, what you're trying to do is make your calculation or your integral not be a function of the area over which you're integrating. So by just looking at the density, you can calculate the current density, and then depending on the area you have, you can basically get different values. So by just multiplying it by different areas. So this is kind of a little bit of housekeeping definition here. Here, this says, talks about convection and conduction currents. I don't know if you guys have heard of convection currents, and I had never heard of a convection current before. So I had to look that up. And so a convection current, so this is convection versus conduction current. So in all our sort of electrical wire systems, we have conduction current. That's why we talk about conduction. Convection is when, so like the example for a convection current, which I can't imagine a case when we're, as electrical engineers, we're going to really run into it, is when, say, you have charged particles in a cloud and the cloud is moving. So basically you get a change in charge with respect to time going through space because the cloud is moving through space. So the charged particles themselves are moving along with whatever is charged. That's called a convection current. And the conduction current is more in the sense that the electrons are moving sort of through the material. For example, like in a wire, you basically get electrons moving through the wire, and that's called a conduction current. And that's what we always run into. So the current density is the conduction current density and not the convection current density. So, I mean, again, it's like something they're defining. I'm not quite sure. I guess we all kind of know that we're not really in the convection current domains in electrical engineering issues. I think this is just sort of they're completing what a current is, or defining what a current is. One really important thing about current is when we're talking about, so for example, we're talking about charge, a current with charge moving, a volume of charge moving through a wire. It's not the same electron moving all the way through the wire. Okay. What happens is basically you end up, with, it's sort of like electrons are moving, maybe nudging along in little increments. So the electron that sort of goes in one end of the wire for that unit of time isn't really the electron that's popping out of the other end necessarily. It's sort of the sum total of electrons going into any space with respect to all the electrons popping out of the other end is what's called the sort of the current. And the important reason for that is electrons actually don't move. I mean, they move pretty fast in material, but if you actually think of a free electron moving through a material, so material like, aluminum, like a chunk of aluminum or a chunk of a metal, let's say, if you have electrons moving through it, the electron is it's not like an electron moving through a vacuum under an electric field. The electron is hitting the atoms of the lattice, And so the actual velocity of an electron, of an actual electron, is limited. It's pretty high. I don't know how to really think about it in terms of what we normally have in life. I just know of it in terms of mobility and velocity. We'll define those in a little bit, but it's limited. So it's not like an electron is shooting across and that's the current, but so the electrons under the electric field influence are just kind of moving across, and it's not that, because current, you can think of it as basically like kind of instantaneous current, but of a section of a line. But really it's that instantaneous current is coming from what came out of that section of the line, and it's not like the same electrons. Okay. Okay, so we just defined the charge density and the current density. So now we want to talk about sort of the electric force and electric field. So Coulomb's law tells you the force between two, this is kind of defining an electric field, but Coulomb's law by itself is very similar to this. So it gives you the force of an electric field is the attraction or repulsion between two charges. Or so if I have a charge Q1 and a charge Q2, and if they are a distance of r away from each other, the force between the two is defined by multiplying the charges together, dividing by 4 pi times this epsilon, which we'll see what that value is in a little bit, and then times over the distance squared. So what this tells you is the force between two charged things is proportional to the amount of charge, depending on if the charges are of different polarity. So obviously you can have positive and negative charges. The force is going to be negative. So if either Q1 or Q2, but not both, are negative, if they were both negative, then Q1 times Q2 would be a positive value, obviously. So if either Q1 or Q2 is negative, the other one positive, we get a negative value for the force, and a negative value for the force means that it's an attractive force. The two particles are attracting each other. And if the force value is positive, it means that they are going to be repelling each other. So like charges repel and different charges attract. So that's what that Q1, Q2 on the numerator says. And also says that the force is proportional to the amount of charges you have in those two particles. Then we have this 4 pi epsilon thing. Again, I think this is epsilon. You'll see in a second what that is. The other part of the force is that it's a 1 over r squared. So as the distances between the two charges get bigger, the force goes down very, very fast. This 1 over r squared function is pretty strong. So basically you have this thing as something that is 1 over r squared dependent on distance. Okay, so this is really Coulomb's law here. And then from force is mass times acceleration. So basically what you actually measure in the real world, if you wanted to see Coulomb's law in effect, is you would see, you'd have two charges that somehow you could isolate as well as you could, and then you try to keep one not moving, and you'll look at the acceleration of the other one, and from there, and the mass of the charge or the charged particle. I mean, if it's just one electron, will have a certain mass. If it's if it's some kind of material, will have some mass. You'll measure its acceleration, and from there, you can actually get the values of the charges, etc. So That's Coulomb's law. Now, because so historically, this is very confusing to me. Hopefully, I'm not gonna be, by saying these things, I'm not gonna confuse you guys more. But this whole business of electric field, I was always confused me as the meaning of force, electric field, and so on. But basically, the thing that us as humans, experimentalists, can really measure is acceleration. Okay, so that's what we can really measure. We can't directly measure the electric force. There's like nothing we can measure the electric force with, right? All we can do is measure acceleration or put a spring on the basically all you can just see how something is moving. That's your only measuring thing when it comes to an electric field, really. So from there, you're extrapolating. So you're measuring A, okay, in an experiment. From there, you're getting the force and using Coulomb's law, you realize whatever, like, what the charges are on those two electrons. So the electric field, along with gravitational fields, were, these things were both discovered. I'd say the electric field was, I guess, these electric fields, like in terms of Coulomb's law and stuff, I think it was in the 1700s, say. And I think gravitation was around the same time, 1600s, 1700s. I don't really exactly remember when. It was when people couldn't get their heads around what's the meaning of a force at a distance. So think about what you're normally, or what people back then normally would think about, is if I'm pushing something, that's, I'm exerting force on it, but my fingers are connected to the pen. So I'm exerting a force on the pen, but I'm connected to it, physically connected to it. This something like an electric field, or objects, or like, sorry, not something like electric force, Coulomb's law, etc., is the charges are exerting a force on each other without actually being connected to each other. So people, I guess people still do have, people like myself have a hard time visualizing how that's sort of possible. And at that point, people didn't have a model for it. So they came up with the idea, this is entirely an idea of defining a field, and they called it the electric field. Okay, so because again, they were like, they were came up with the thought, the theory, that there was a field generated, and that field is the way they defined it, is if I have a so-called test charge. So you get the E field, you get it from Coulomb's law, from Coulomb's law. So Coulomb's law, this guy comes first, and from this, they got the electric field idea to try to get their heads around sort of force at a distance. They thought about what would happen is if I had a charge in isolation, and then I had a so-called test charge. Okay, that would be, so let's say Q1 now in our Coulomb's law ends up being this thing that's creating this so-called electric field. And then I would have a test charge, and I would basically move that test charge all along space, like at every point in space, and calculate the force. And that test charge would have a unit of 1. Okay, so then at any point along the space, I would have the value of this field, which is the electric field. Okay, again, I'm probably confused you more than I clarified anything, but that's why the electric field only has the single charge value, and they're pretending like they're taking a test, quote unquote, test charge with a charge of 1, whatever that is, moving it around space and calculating the force on it and getting that for every point in space. And that gives you the value, that gives you an electric field that is a vector element. And it's, so electric field is a vector field, and it's basically defined in the entire space. And it's a function of the charge that's generating that electric field and the distance away from that charge. What else do I want to say? So, and then if you had the direction of the electric field is in the radial direction away from this charge. So at every point, so you see in this graph, at every point, the direction of the electric field is away from a positive charge. If you had a negative charge, so if I had a negative charge here, then the electric field lines would be going towards the charge. And one way to look at the electric field lines is if you had positive charge, the positive electric field lines would push you, away along the direction of, basically away from the electric field. And then if you had a negative charge, you would get pulled in the opposite direction of the electric field. Okay, so basically this Q prime is the test charge. And so this force on that test charge would be the test charge multiplied by the electric field. And notice it's given in newtons, which is unit of force. Okay. And then they also define the electric flux density D as being this epsilon factor times the electric field. So that would be one way to at least get rid of this thing on the denominator by just looking at D. Okay, so that's the electric flux density. And this epsilon factor, epsilon 0, is so-called permittivity of free space. And it's given by this value, 8.85 times 10 to the minus 12 farads per meter. And, I probably have to look that up once a month or something like that. I use it all the time in calculating capacitances. So anyway, but one thing, by the way, to be careful about when you are looking that up, I've made this mistake, is really be careful about the units. Because this permittivity of free space is, if you're looking it up on Wikipedia or whatever, it's given with different units, and you better make sure you've got the right units. Otherwise, you're going to end up with things that are, thousands and thousands of times bigger or smaller than they should be. And usually we don't have a feel for what it should be at this point in your career. So you just sort of do the multiplication, you end up with a really gigantic or really small number because you selected the wrong value when you looked up at the permittivity of free space. That's epsilon naught. Epsilon, then each material has a so-called relative permittivity. So that's this epsilon R. So epsilon naught is just one number for everything. And then this epsilon r is something that has no units, that depending on what material your electric field is inside, you'll have a different permittivity, relative permittivity for that material. And we'll look at some different values for that. So that's kind of how permittivity is defined. Usually, the total dielectric constant, this epsilon, is independent of the magnitude of E of the electric field, and you call that a linear material. And usually it doesn't depend on which direction E is pointing, and that's called anisotropic material. But if it is dependent on the direction of electric field, it's called isotropic electric field. And if it was dependent on the magnitude of the electric field or the electric flux, then it would also be called nonlinear. So I guess most materials are kind of like those, but we kind of ignore that for a lot of materials, like let's say if it's a cladding for your coax cable or the FR4 material, you kind of ignore those things. Okay, so the electric fields, fortunately, have this really nice property that basically you can apply linear superposition of electric fields, meaning that let's say you had a situation where you had not just one charge in space, but let's say you had a bunch of charges sort of distributed, minus q all over space. What you would do is to calculate the total electric field is basically you'd calculate the electric field for each one of those and basically sum them because of this linear superposition. So you'd sum the vector fields and get the total electric field caused by all these different charges all over space. And this turns out to be, very, very useful behavior by the electric field. That basically what it says is the electric fields are not really interfering with each other. Basically, you can just assume that for each charge, you can assume it's just sitting there by itself, calculate its electric field, and to find the total electric field, you sum all the electric fields up. So, and then again, this just says you can keep going for different charges. And in fact, if you don't have individual charges, but a distribution of charges, you can do the same thing. So this is like summing. You had individual charges, you would sum them. And if you had a continuous density of charges, you would end up doing an integral. So you do a volume integral, line integral, or surface integral if you had a continuum of charges. Oops. Okay, so this is actually kind of a cool example, but this is like, it gets up to be really painful. What you do is, this is sort of a typical example of figuring out the electric field caused by like a ring that has uniform charge density and the electric field along the z-axis. And if you do this, basically you're gonna basically calculate you're doing a line integral and calculating the charge along string and the effect on the electric field. And anyhow, you'll kind of a fun exercise, I guess, but I'll skip it. You guys can follow that later. Okay, so let me stop here. We can take a little break. Let's say a 10-minute break. We'll get back at 9:20 and talk about Gauss's law. So back to the lecture. Everybody can hear me okay? Can you guys hear me?
I can hear you.
Okay, great, thanks. So whereas so Gauss's law is what made it into Maxwell's equation. So although Coulomb's law is really fundamental for electric fields and electric force, Gauss's law isn't really a fundamental law, but it's kind of what's quite useful and what ended up being in Maxwell's equation, which is this divergence of the electric flux density. The divergence of electric flux density is equal to the charge density. So this, again, what this says is if I take a volume and I look at all the electric flux lines coming out of that volume, so the entire volume, if I integrate all the flux lines coming out of the volume, that total value is going to tell me the entire, charge inside the volume. Okay, so basically this equation is what's kind of coming out of this thing, is if I had some kind of, and the volume, by the way, that's enclosing. So let's say if I had, let me just show you guys how this is useful. Let's say I had some kind of object that was shaped like the funny shape, like a potato or something like that, a misshapen potato, and it had some charges in it. And I wanted to figure out what that charge was. Okay. Taking the surface integral along this misshapen shape, this volume, this weird volume, like any volume, would be a really difficult task. It wouldn't be easy at all. But I don't have to take this integral, this flux integral, along that volume necessarily. I can define another volume that's not so misshapen. So I can take, so this basically has, whoops, this will have a bunch of electric field, or remember there's the electric field, and the electric field and the electric flux density are only related to each other through this epsilon. So really it's the same thing when I talk about the electric field or D factor. We just have to make sure we got this permittivity number in between, but you guys get the idea. So, but what I can do is I can define a really, really simple surface that I can integrate around. So for example, I can take a perfect sphere, imaginary perfect sphere around this, measure the flux lines along that sphere. So integrate the electric flux lines around that sphere and get the total charge inside this misshapen volume. So nothing tells me that I have to take this flux lines right at the surface here. I don't have to do that because that would make for a very, very difficult surface integral to do. I can take a step back, define a shape I like. That, again, the sphere is popular for something like this because it's, easy to take, a sphere. We can kind of relatively easy take the integral along the sphere and define it, and take the flux lines along the sphere, integrate them, and I get the total charge inside the volume. So this is actually Gauss's law, although it's not, fundamental. It's very, very useful in the way we can, I was just, honest to goodness, in our startup, we were trying to figure out a, capacitance issue day before yesterday, and we ended up using Gauss's law to try to reason through what would be a reasonable value of capacitance. And it really comes, in my mind, the main usefulnesses of Gauss's law is the fact that you are free to define the surface away from the object. So you're always trying to figure out some kind of a charge, and you can define a surface away from that charge as long as that surface doesn't include any other charges, and do your integral on that sort of imaginary surface. And that imaginary surface is called a Gaussian surface. Okay, so again, it's not the surface of the thing itself, but a surface you defined. It has to be a closed surface, so it can't be like a circle or something like that, or a ring. It has to be a sphere or a like ellipsoid or something like that. Whoops. Sorry, guys. I lost my thing. Sorry, guys. So it has to be a closed surface, and then I can basically get the total charge inside. Okay. So basically, this is the differential form of Gauss's law that we had written up as part of the Maxwell's equation. If it was the first, it was the first equation, Maxwell's equation, and basically using the definition of the divergence, etc., you can get the integral form of the Gauss's law. And again, the integral form is where really sort of shows what I was just saying, which is you're taking the electric flux lines and integrating them along a surface, a closed surface, and that operation gives you the total charge enclosed by that surface. Okay, and again, this is called, this is called the Gaussian surface S. And the important fact there is that can be whatever you define yourself, as long as it's an enclosed surface that's completely enclosing the charge. It can be whatever surface that's easy to calculate an integral around. Okay, so here's an example of how this is done. I'm not going to get in there here. So okay, so that is Gauss's law. Again, it's sort of the first equation in Maxwell's equation. The use of it is you can use it to calculate the total charge in some place in space. By the way, this also tells us that this, when you're doing the surface integral and you get a charge, it tells us that the electric field is caused by, basically it says that there is, or implies that there are isolated electric charges. Okay, because if I was going through and taking these integrals, if the charges inside weren't isolated, that they would have to, by definition, be in a continuity. I would never be able to enclose the charge. So because I'm able to get some value when I'm enclosing a volume, I get that there has to be isolated electric charges. Otherwise, you couldn't do that. And notice that it's not called Gauss's law, but then we have a corresponding law, which is del dot B is guaranteed to be zero. This was the third line in Maxwell's equations. And that says that there are no isolated magnetic charges, because I can never, no matter where I close my volume around in space, I can never, that's always going to be zero. I'm never going to capture a magnetic charge because there is no such thing. Okay. So this is kind of an implication about the nature of sort of magnetic charges, which we have not found in nature, and electric charges, that we do see. Okay, so that was Gauss's law. Okay, now here's another interesting thing, which is that just as, when I talked to you guys that when we're looking at Coulomb's law up here, what I was telling you guys, what I was trying to imply, that the real thing is acceleration, velocity of something. Okay, that's what we can actually measure and know, that's a real thing. So that from there we calculate something called a force. And from there we calculate something called an electric field. But as you can't measure an electric field directly. You can just measure acceleration directly, acceleration of a charged particle. So meaning that these, to me, an electric field is a way, like sort of a mathematical tool. I guess I don't know how to put it to visualize this thing. Kind of a mathematical tool to try to figure out how charge would interact, what would be the force of a charge. Okay, but as you move away from the acceleration concept, as you're moving from acceleration to force to field, you're getting further from something you can actually measure and getting closer into sort of a mathematical construct. I don't know if that makes sense or makes you guys more confused, but that's how I look at it. So these are all, in my mind, there is no such thing, really. There's no such thing as an electric field. It's basically something we've created, a concept we've created to help us understand the acceleration of a charge in the presence of another charge somewhere in space. Okay, so again, I don't know, that might confuse you guys more, but so that's, the electric field is like twice removed from reality, and this electric scalar, and it's basically a construct to help us to make the math easier and to measure that so to predict or measure that acceleration, to predict that acceleration better. That's what electric field is. So the voltage potential or voltage is even one step further removed from reality. And notice that when you guys are in the lab, when you're not taking an E&M field, you're actually never working, you're never like measuring an electric field. But you have voltmeters, right? In the lab, you have voltmeters, you have oscilloscopes. These are measuring something called voltage, something called electric potential, okay? Voltage potential. So that is sort of the next level of abstraction, because that voltage, I should have put it so it's not so confusing, but that voltage is really sort of a measure of the electric field. It's not the electric field itself, just as the electric field itself is not really the acceleration, but it's like a sort of a construct. And so why are we measuring what is this voltage and why is we measuring it? So one thing is, notice that whereas force, so acceleration is a vector, force is a vector, electric field is a vector, voltage is not a vector, it's a scalar, right? You never say this thing is 10 volts and pointing left or pointing right or pointing in this angle. You just say this voltage difference, or this voltage is like 1 volt or 0.5 volts, etc. So voltage is a scalar, and the reason it's useful is because it is a scalar. So like in the lab, you can measure this thing. It's a scalar value that's easier to measure and deal with. And then from it, you can sort of calculate the electric field later. So that's why that's what voltage is. And so voltage, the definition of a voltage is sort of voltage is a measure of the potential energy that a charge would have working against an electric field. So for example, let's say I had an electric field caused by a charge Q plus in space. And let's say I had another charge Q minus, and I brought it from point A to point B, sort of closer. So let's call that Q plus, sorry. So it's a little bit easier to think about. So I brought that Q plus closer by a distance, closer to sorry, we'll call this Q1, call this Q2. So I brought Q2 closer to Q1 by the separation distance between A and B. So because those are repulsive charges, I would have had to work against that electric field. I had to put some work into that charge to bring it closer, to bring Q2 closer to Q1. I had to do some work. And at that point, that charge, as soon as I let go of that charge, it has some potential energy. It's going to go back to back to A, or literally it's going to just go to infinity far away. But let's say initially it's going to go back to A. So there's some potential energy that charge gained from going from A to B. Okay. And that difference gives me the potential energy difference between the charge sitting at point A and charge sitting at point B. And that potential energy difference is called the voltage or voltage potential. Okay. So, and it's given by, this is a function of distance, a change in voltage. By the way, we always talk about when we're in lab, we're always mentioning something as 5 volts or 2 volts, etc. A potential is really a differential thing. So you have to say that, you don't have to say it because we have sort of a shorthand way of talking about it. Is you'd say a potential difference between 2 points is 5 volts or 1 volt or something like that. That's really the way to put it. So when in the lab, by convention, when we say, and you'll see this in a minute, when we say something is 5 volts, what we've done is we've sort of created this concept of a ground. So a ground is a point where that charge sort of feels no potential energy. Okay, so in free space, that ground would be at infinitely far away from our charge. But in the lab, it might just be the ground line where that charge doesn't feel any potential energy. And so we're defining the potential difference from whatever point we're measuring to that ground. That's by convention. But really, potential is a differential value, as you see in this equation. Okay, how it's defined. And basically, it's the dot product of the electric field sort of along the length of the line, looking at sort of that charge. So if I was just going to be, my electric field was pointing in the direction of L, so it would be E times L, and E would be voltage over distance. So we'll see that second. Okay, so the reason we can do that, this slide, I don't like this slide because it's implying that it's really the other way around from what this slide is implying. So it turns out that luckily, the reason we can use voltage potential is that the electric field is conservative. It's not guaranteed that a vector field has to be conservative but the electric field is conservative. So what does being conservative means? It means that no matter what path, so let's say if I take an electric field around any closed path, okay, as any closed path, always come up to zero. So let's say if I was going from this point P1, go along C2 and come back to P1, whoops. Why did that make, sorry guys. What was that? So, uh-oh, did I get in the PowerPoint? So regardless of the path I take for an electric field, going from A to B and back to A. So if I went in a circle to get from A back to A, or I went into a line and came back another line to get to A, and so on and so forth, as long as I'm electric field is conservative, it means if I do that, I always end up basically with zero if I sort of integrate the electric field along any closed point. And because of that, it means that it doesn't matter how I get from point A to point B. Because if I go from A to B along any path and come back to A along any path, that value is zero. It means it doesn't matter how I get from A to B. Okay, so that means I can define a scalar value between A and B, because it didn't matter how I got there, to tell me the potential difference between those. And that's really kind of the magic of having the potential. So voltage defined, again, it's a differential. You always have to say, to be correct, between two locations. So voltage difference between two locations is, integral of the electric field as a function of distance along that. So between those 2 points, it could, the shortest path between those 2 points is fine. And that's the potential difference between those 2 points, or the voltage between those 2 points, as we like to say. And so this, by the way, this says, this slide, the main thing I want to say about this slide was that it's saying that by convention, we call, a point in infinity, we call the ground, assign it a zero reference voltage just for convenience. And so that, we could potentially have a voltage at a point when you're referring it to infinity. And so when you're saying like 5 volts only, and not a potential difference of 5 volts between those 2 points, you're implying that you're comparing that point's potential to infinity, or someplace where there's zero reference, 0 volt reference. Okay. And so, so a lot of times, sort of shorthand for me, if I have, let's say in the case of, do we have parallel plate? Let me just find this very useful, is jump through these guys. No, it's too far away, but let's say I run into parallel plate capacitors a lot. Okay, so let's say if there was an electric field between 2 points, like you would have, two parallel plates, and you had an electric field between those 2 points, and there were a separation D apart. So the electric field would be the voltage, let's say measuring a voltage between those 2 points, would be the voltage divided by distance, or the voltage would be the electric field times distance, and there's like a negative sign here. So the electric field, so if this is 5 volts, this is 0 volts, so there's a potential, this is a potential difference of 5 volts from the bottom plate to the top plate. The electric field, because of this negative sign, the electric field would be pointing in the opposite direction as that. That's kind of always is all like useful stuff for me to remember. All right, so that's electric field and potential. Some examples here. Okay, now we're talking about, so we talked about electric field, now we're talking about back to being currents. So it turns out that, again, the current density is current per unit area going through a material, so the current density. And the current density is proportional to, the current density is a vector. So yeah, notice it's a vector. This is in capital, sorry, it's in bold values, and it's related to the directly related to the electric field through this constant called conductivity. So this is conductivity. And this conductivity is different between different materials. So for example, here's a list of some common conductors, and silver, copper, iron, aluminum, etc. And you see that conductivity values there. Then there are also conductivities given for insulators. So those are where you wouldn't get such a great amount of current flowing if you had the same electric field. And notice these are, as this thing points out, as much as a factor of 10 to the 24 difference between some of these insulator values and the conductor values, okay? But it's sort of all the same function, is that the conductivity is relating the electric field across some material to the current density along the material. And interestingly, semiconductors, which I work with quite a bit, are sitting somewhere in the middle between conductors and insulators. That's why they're called semiconductors, not fully conductors. Okay. Now, a perfect dielectric or a perfect insulator has a conductivity of 0, but notice that none of these things, we were used to thinking of, glass not conductive, conducting, etc., electricity, but it's still not really 0. It's a very small number. So only a perfect dielectric, which we don't have, has a conductivity of 0. And in the same way as when we think of a conductor, we think something that has, perfect conductivity, like of conductivity of, an infinite value. And notice that, the stuff, even copper, we use copper wires a lot. As like trying to have a good conductor, use copper. And there it has a very large conductivity, but not infinite. Okay, so this is what conductivity is. Okay, this talks about conductivity and semiconductor, which is kind of interesting, but I'll skip that. This is like very important to me, but we can kind of not necessarily think about it in this class. But going back to this, notice that if you had a perfect insulator, so if the sigma conductivity was 0, you would have 0 current no matter what the electric field was, you would have 0 current in an insulator. Okay, so that in a perfect dielectric, the current would be 0. Okay, and then vice versa, if you had a perfect conductor, so if sigma was infinity, means that, so how do you get sigma to be infinity? Sigma would be infinity if 1 over sigma is epsilon over j, and this thing would go to 0, and you'd have sort of, you'd need to have sort of an infinite, sort of infinite current, let's say, okay, or in a conductor, because you're going to have current through it. So basically, in a conductor, in a perfect conductor, you cannot have an electric field at all, which is kind of interesting. So basically, regardless of what the current density is, in a conductor, in a perfect conductor, it would have no electric field. And in all cases, you have, even when you have an electric field in a conductor, it's a very, very small value, practically 0. That's pretty important. This sort of gives us the resistance equations, defining it in terms of the electric field and current density. I think I'm just going to jump to the conclusion here, which is that it's basically resistance is, what the heck? For some reason my resistance is proportional to the length of a wire, is how I look at this. So it's proportional. L is the length here. So the longer your wire is, the higher your resistance, and it's inversely proportional to the wire or conductor area, surface area, and is inversely proportional to the conductivity. So the higher your conductivity, the lower the resistance of a wire. This example is really sort of useful. So remember that our goal was to go back to our transmission line equations. For the transmission line equations, we had a resistance, we had an inductor, we had a capacitor, and then we had another resistance sort of sitting here for a full lossy conductor. So the resistance along the wire, so this would be this value here, would you define what's in the previous equation, and you can basically use the same equations to figure out this value. An example for a coax cable is given here. Notice the one thing here that's a little confusing is you're calculating the resistance through your dielectric. So you're calculating this resistance, which is going to be very, very high, but you need it anyway for a lossy transmission line by using these equations for resistance. Okay, so you can basically, using those, you can figure out the resistance for a transmission line. Just going to jump over Joule's law. Talks about resistive sensors on bridge. Okay, so now we want to basically get to capacitance, which is kind of the main thing I wanted to talk about, which is, again, like if you have a transmission line, you have a capacitor per unit length. We're going to talk about the inductor in the next lecture, but the capacitor sort of like the main item of discussion for this lecture. So how do you calculate that? Okay, so capacitor is really kind of something you think about like being in a more of a dielectric material, having capacitance, because as you'll see sort of the definition of capacitance, it doesn't really, inside a conductor, it doesn't really make sense to have, no, I guess there is some capacitance inside the conductor as long as you have an electric field. But anyway, like dielectric material, the way you end up with an sort of electric field on a dielectric material is that when there is no electric field in a dielectric material, the electrons for each atom in the material, the electrons are like sort of distributed evenly around the nucleus, and you end up not having an electric field in any direction, because if that if for if for this guy I have my electrons uniformly distributed along the nucleus being a charged particle, sort of all the electric fields cancel each other out, and I don't get any net electric field in this atom. And if there is zero external electric field, this is just sort of a neutral thing. It's not generating anything. So, but in the presence of an external electric field, what happens is the electrons tend to remember that the electrons being negatively charged, if I have the electric field going in this direction from bottom to up, the electrons are going to move from top to bottom. So generally they're going to be more, they're going to not, the nucleus essentially isn't going to be centered for that electron cloud. And you end up having this sort of, if you think of the center of the cloud having this minus charge, effectively, you end up with what's so-called dipole. Basically, you end up with having the atom itself having a separation in some sense between the positive and negative charges. It's not fully a separation, but it's like sort of a preferred distribution of charges in a dielectric material. And that's kind of how you end up with this sort of dielectric materials ending up supporting an electric field, and sort of how they react to it. I'm not going to talk about polarization, because not all material are able to get polarized. It doesn't really, we don't necessarily deal with, you get polarized capacitors. I see that less and less. So mostly what we deal with isn't really polarized, really. But one thing that you do have to worry about in capacitors of all types is breakdown. So if you put too much electric field across a dielectric field, the material can actually break down. And so there's something called the dielectric strength, but usually what you see that as is like a rating or a breakdown electric field, where they say, hey, don't put, like, if you have a capacitor with a certain dielectric thickness, don't put more than a certain voltage across it, or it's gonna basically break down. You'll get a short, you'll damage your capacitor. And so you basically have to be worried about that. There's like ratings on capacitors. 5 volt, 3 volt, 20 volt breakdown. So do pay attention to that when you guys get into the real world and are designing with capacitors. Do pay attention to the breakdown, electric breakdown. Now, electric breakdown, again, one of those things where it seems like the electric field for breakdown is always in like megavolts per something. So it seems like a gigantic number that you'd never run across in the real world. But the problem is this over meter thing. So it's megavolts over meter, but like the capacitor, the dielectrics in your capacitors are like never a millimeter thick. They're usually in the micrometer thick. So 1 times 10 to the minus 6 or something like that meter thick level. So this, what seems like a gigantic electric field, is actually usually a pretty small voltage, something like single digit volts or maybe double digit volts. Okay, so again, be really careful about that. It's really easy to exceed those numbers. I'm going to jump over the boundary conditions. Just a couple of things that are important that comes out of the boundary conditions is that for a perfect conductor, there is no electric field inside a perfect conductor. Okay, so this ends up being very, very confusing. I haven't, because usually thinking about, well, how am I getting current on a conductor? I'm putting a voltage difference between two points. What's the voltage difference doing? It's creating an electric field through that conductor, and that gives me a current. But that's like more of it's just something that you can think of with a non-perfect conductor. If you have a perfect conductor, you could not have an electric field across it. So, and sort of the net electric field inside a conductor is always zero. So just, again, I've never managed to like really be able to fully explain this, but again, just remember that an electric field, a perfect conductor is not going to be able to support an electric field. And then the second thing that's a useful thing to remember is because of that, every electric field, when they terminate on a conductor, it has to be perpendicular to the surface of the conductor. It can never be at like a tangent to a conductor. So like if you had, what I mean by that is if this was a surface and I had an electric field terminating on it, it would have to always be vertical to that surface. I can't ever have sort of a grazing. It's possible to have it, but like it means it's not a perfect conductor, etc. But this would not be like allowed if having a non perpendicular direction of electric field on a conductor. All right. So finally to capacitance. And capacitance is actually kind of comes from this definition, which is kind of a strangely simple definition. It says that if I have two conductors in space, or two conductors basically separated from each other, and if I put a net charge on those two conductors and measure the potential or the voltage difference, the potential difference between those two conductors after I put a certain number of charge between the two conductors, that value, so the charge over the potential that charge created, I get this gives me something called a capacitance. So that's really sort of all there is to it. Is it comes from capacitance comes from that definition. No integrals, nothing like that. Just that's the sum total of it. So there's of course like different ways of looking at this thing. If you know the capacitance and you put a certain voltage on that capacitor, you can calculate the charge, or if you know how much charge you were able to put on a node and measure the potential difference, you can calculate its capacitance. So there's like a lot of like different ways to this equation is enormously useful in circuit design, obviously, and there's a lot of ways to deal with it. But that's sort of the definition of capacitance. So this says, if you have I don't know what the slide is trying to say, honestly. I've never this simple relationship between resistance and capacitance. I've never used that. So anyway, so I think this is like the point I was trying to get to, and of course like the next example, but this is like a simple geometric situation. Parallel plate capacitors, you actually run into this quite a lot. So fortunately it's a simple type situation to calculate, and then fortunately run into this a lot as opposed to some other really complicated scenario of calculating capacitances. The reason is in a printed circuit board, a lot of times you have a situation where you have two metal lines separated by dielectric. And as you'll see, you have something similar to this in a coax cable. So but for a transmission line in a printed circuit board, this is pretty typical for your line, trying to calculate the capacitance of the line. So basically, the reason why it's so convenient is because it's really so simple to calculate the electric field between these two plates. If the two plates are parallel to each other, the electric field lines are running vertically between the two plates. Of course, at the edges of this sort of metal dielectric sandwich, you have electric field lines that are not running vertical. But if, and this is usually the case, sometimes it's not, if the area of this capacitor is much bigger than the periphery, you can just sort of ignore the fringing field lines. It's not always the case, and when you start getting into conditions of needing to calculate the fringing field lines, this ends up not being such a simple thing. But again, for most cases, you can ignore the fringing field lines because the area is much bigger factor than the periphery. Okay, so again, the nice thing is it's easy to calculate the voltage. The voltage is just the electric field times the separation between the plates. So that's pretty easy to calculate. And and then, you can basically, the electric field lines also is basically using Gauss's law. You can calculate the field in terms of the charge. Okay, if you pick a surface here, like a Gaussian surface, and calculate the electric field around it. So it's really easy to do that. And you end up with this equation, which is sort of worth memorizing, for me anyway. It's been worth memorizing, which is this capacitance for a parallel plate capacitor is area over the separation between the two plates times the dielectric constant of the material between those two plates. So just, again, my recommendation is to remember that. Anyway, I use that all the time for calculating capacitances. Okay, so again, if you had a transmission line on a printed circuit board and you wanted to calculate the capacitance per unit length of the material, you'd have to figure out, so that would be, you'd have a top metal, bottom metal line for your transmission line, and then you'd sort of calculate the area, the separation between those two, which is given to you by the manufacturer, and multiplied by the dielectric constant of the material, and you have your capacitance for your transmission line equations. And then if you have a coax cable, it's a little bit more complicated, but not much more, because to calculate the capacitance, basically you're doing the same thing. In this case, the calculation of the voltage with the electric field ends up being a little bit more complicated, but again, not much, because the electric field is sort of uniformly cylindrically distributed. So you can calculate the area of the cylinder multiplied by the dielectric constant. So it's pretty easy to get the potential between the 2 points between the outer shell and inner shell of a coax cable to get the voltage. And then same with the capacitance. So same with the charge. And basically you end up with this equation, which is it's harder to remember, so, but it's good to be aware of this equation for the capacitance of a coaxial line. And then you can also get the capacitance per unit length, which is kind of what you generally need for your calculation. All right, guys, so this is where I wanted to get to today. And we're gonna have your quiz in about 5 minutes is gonna come up on the site. I'm gonna stay on for about like 10:30. If you guys have any questions, I can answer that about the quiz or the lecture or anything like that. But anyhow, is any questions about the lecture today? Okay, guys, well, feel free to take a break then. I'll stop the recording here and I'll stay on till thanks. So I'll stay on till 10 till 10:30 in case you guys have any questions. Or if you have any questions afterwards, the quiz is due at midnight, so you can always send me an email. Thanks.